To help us work with these multiple linear regression models efficiently, we need to use some matrix notation. We will look at that in this video. The first step here is that we're going to remove the intercept from consideration. This is not as bad as it sounds. The intercept is seldom of interest, and we can always recover it if we want to know it. We remove it by first stating the regular regression model. Then in the second line, we restate the regression model at the point which we know the model will pass through, the averages. Thirdly, we subtract the second line from the first line. This creates a new regression model, where our variables are in their centered form. In other words, instead of xi, we use xi minus the mean of all x values. Instead of yi, we use yi minus the mean of the y's. Recall that centering is a process that simply shifts the variable, but maintains all of the relationships that it has. When we build our model with these centered x and y variables, or as we sometimes say deviation variables, we now have a model where the intercept is 0 and does not need to be estimated. Notice from the second line over here, we can always recover that intercept value back if we really are interested in it. Now sometimes you will see me build regression models with the intercept in it, especially in the designed experiments part of the course. So you really don't have to do this step, but it does help for interpretation later on. So now we have a model without an intercept, but we have k parameters, beta 1, beta 2, up to beta k, and each of them are multiplied by their corresponding x variable. Right at the end we have an error, epsilon I, and all of that is added up in a linear combination to give you a value of yi. We can express this observation as a linear combination in vector form. Here we have a vector x and a vector beta, and this is for the ith observation. So we collect our vector x, the input data, and the vector beta, and we multiply them using regular matrix multiplication. Add the epsilon value to the end, and then we get our yi value. There are k values of x multiplied by their corresponding k coefficients of beta, and we add those up to get our single y value. And we will call that vector xi to emphasize that that is the row vector for the ith observation of x. Now if we have multiple observations of x, then we can stack those vectors in a matrix and form capital matrix X. Row 1 is the first observation, x1, row 2 for the next observation, x subscript 2, and so on up to the last row, x subscript n. I've also replaced the betas now with b's to emphasize that we're going to estimate the b values rather than us knowing what the population model is. So we have a matrix of x observations, n rows and k columns. There are n rows for every observation and k columns for the k input variables. Multiply that here by our vector b1, b2 up to bk, so k entries of b, and then we add a vector of errors at the end. I've emphasized the dimensions of each of the vectors and matrices over here. Now the objective function for multiple linear regression is exactly the same as regular least squares. Minimize the sum of squares of the errors. If we take that vector of errors over here, lowercase e, the sum of squares of the errors can easily be shown to be E transpose E. Well, that vector E can be written as y minus matrix x times vector b. If we sub that in, we get the second row over here. And if we expand that matrix vector transpose, we can use some basic rules of matrix vector algebra to get this revised objective function. We've seen before that we can minimize this objective function by setting the partial derivative of it with respect to the search variables to 0. This means the partial derivatives with respect to each of the entries in vector b are set equal to 0. This will give us k equations in k unknowns. We have k partial derivative equations, and there are k values of b, b1, b2 up to bk. Now these k linear equations in k unknowns can be solved very compactly using what is probably the best known formula in least squares, that the entries in vector b are equal to x transpose x inverse multiplied by x transpose y. Don't forget that formula. You're going to see it reoccurring several times in this module, as well as in the next module on designed experiments. And it's time for an example now, where we've got two vectors, x1 and x2, shown here on the screen. Let's use these to predict the vector y. The first step we're going to have to take is to center the vectors x and the vector y. We'll do that, and the results are shown here. But before we go ahead and even solve this equation, what do you expect the slope to be for x1 as it relates to y? And what do you expect the slope to be for x2 as it relates to y? Examine the data and write down your answer, keep it aside, and we'll verify it later. Now let's go solve this mathematically and try to verify our intuition. The first step we need to do is assemble those two individual vectors into a matrix capital X. The first column will represent the entries for variable x1. The second column in matrix X represents the second variable, x subscript 2. Notice that we have n observations, 6 in this case. So there must be 6 rows in the X matrix and 2 columns, one for each of the input variables. X is always an n by k matrix, and the y vector is always an n by 1 vector of the output values. These are assembled now as shown here on the screen. So we are ready to go calculate vector b, the two coefficients of our regression model. X transpose X inverse multiplied by X transpose Y. Let's go calculate the first part, X transpose X. That's shown over here. Then we can go calculate X transpose Y separately, shown over here. You're welcome to use any software tool to do this, but here on the screen are the R instructions in case you wanted to try it over there. But we actually need the inverse of X transpose X, and you can also do that in R with this line of code. So now we have X transpose X inverse, and we can go multiply it by X transpose Y. I want to point out that X transpose X will always be a k by k matrix, k being the number of variables in our model. In this case, k is 2. It is going to be an important point later on that the entries in X transpose X represent the covariance of the X variables with each other. For example, the entry in the 1, 2 position in this matrix is the same as the entry in the 2, 1 position. That's because the covariance of variable x1 with variable x2 is the same as the covariance of variable x2 with variable x1. You'll recall that from an earlier video, and that should be the same number. The entries on the diagonal are also covariances, but they're covariances of the variables with themselves, so we simply call that variance. In this case, the 55.5 over here is directly proportional to the variance of the x1 variable. The 62 is proportional to the variance of the x2 variable. Because the diagonal entries in X transpose X are variances, they should always be positive. Variances are by definition positive values. And the off-diagonal elements in X transpose X will always be symmetrical. Once you've calculated the upper diagonal part, you can just copy the values over to the lower diagonal part. Now here's a question I want to leave for advanced students. What will the X transpose X matrix look like when the variables x1 and x2 and so on are entirely uncorrelated with each other? What will you observe in those off-diagonal entries? You'll see the answer to that coming up in the next module, but you should be able to guess what it is now. Now, if X transpose X represents variances and covariances, what do you think the entries in X transpose Y represent? If you guess that it's the covariance of the entries of X with Y, you're right. The first entry in the X transpose Y result is the covariance of variable x1 with Y, and the second entry is the covariance of x2 with Y. Now take a look at the signs. Do they match your expectations, what you wrote down earlier? Look back at the raw data and make sure at least that the sign information matches your expectation. Remember, right at the start of the section on linear models, we said that for covariances, at the very least you can interpret the sign of that result. The magnitude of the value isn't so useful. And those results that we see there, the 36.5 and the minus 36, seem to make sense. The positive sign for the first entry indicates that the first x variable is positively correlated with the y variable. And we see that in the raw data. As that first column increases, the column of y also increases. The second entry in X transpose Y is negative, indicating that that column in X has a negative correlation with Y. And that's also observed in the raw data there. Now, one final thing to mention before we end this video is that you should never calculate your least squares model using this X transpose X inverse formula multiplied by X transpose Y for real general data. It works in some specific cases very well, and that's why we will use it later on. But in general, there's very poor numerical conditioning with calculating the inverse in this way. Sophisticated least squares packages, such as R, will calculate the linear model using the QR decomposition instead. It's a similar type of linear algebra step, and interested students should go investigate that in their own time. The R software package uses the QR decomposition behind the scenes and not this inverse. And since we're talking about R, let's go see now how R solves this example problem. Use the lm command and say y is regressed on two variables, x1 plus x2. Try that out and use the summary command on that model result to see if it matches the output that you calculated with the x transpose x inverse x transpose y equation. There is one last entry we need to go calculate, and that is the standard error. Standard error, you will recall, is equal to the objective function of the least squares model divided by n minus k, and then we take the square root. So in other words, standard error is calculated as E transpose E divided by n minus k, and then we take the square root. Once we have that error vector, it is easy to go calculate the standard error. In the next video, we're going to look at the important topic of interpreting the multiple linear regression coefficients.